Hello everybody, this is the video clip for chapter 5 and we are in the section 5.4 which is the so-called approximation. Okay, actually this one is the application of the uniformly continuous. Okay, so the first thing that we are going to do the approximation is that like we are going to approximate the continuous function, especially the one that uniformly continuous by the so-called step function or the constant function or piecewise constant function. Okay, so the step function, a function s from the closed interval a b to the real number r is called a step function if your interval a b can be written as a union of interval I1, I2, I3, etc. to In, such that the infimum of the I subscript I and the infimum of the I subscript j is empty. So basically, or the interval is not intersect each other. Okay, and there are a real number c1 up to cn such that each each function value at each interval equals to that constant ci. Okay, so for example, your s can be a function from negative 2 to 4 to a real number r, where your s, okay, defined piece by piece, okay, by this one 0 if your x coming from 2 and go to negative 1, and it can be 1 if your x is from negative 1 up to 0, and it can be 1/2 if your x greater than 0 and less than 1/2. It can be 3 if your x is starting from 1/2 and less than 1. It can be negative 2 if your x is greater than or equals to 1 and less than or equals to 3, and it can be 2 if your x is greater than 3 and less than or equals to 4. Okay, and you can imagine that the the graph of this function will be like will look like a step or a ladder. Okay, so for example, from negative 2 to negative 1, okay, it takes value 0 to 0, right? So here you are going to do the black dot, and there you are going to do the white dot, so that the black dot, it means you include that particular point, okay, but the white dot is mean that you exclude that particular point. Okay, and then from negative 1 to 0, okay, it takes the value of 1. Okay, so you can put it here, okay, as a 1. And from 0 to 1/2, okay, let's say here is a 1/2, it take a value of 1/2. So and it is exclude this point 0 and also the point 1/2. From 1/2 to 1, okay, it takes value 3, so it go a little bit beyond here. Okay, so let's say that here is 3. Okay, the level of 3 is up there. Okay, and then from 1 to 3, okay, it takes a value of negative 2, so it go down. Okay, all right, over here. And then from 3 to 4, it takes the value of 2, so it coming somewhere between the 1 and the 3 right here. Okay, so this is just roughly speaking that it is like each piece, okay, of this function, it is a constant. Okay, and our theorem saying that if you have a function f that is from closed interval a to b, and it is a continuous on this closed interval, then no matter how epsilon, like how small the epsilon is, we can find a step function, okay, depends on that epsilon, so that the difference between your f and that step function is less than the epsilon that is given for all x in that closed interval. So it means that you can approximate, okay, so this one is the approximate value, okay, you can approximate your function f, okay, by this step function s, okay, within any error. I mean, no matter how small the error is, you can find a step function that satisfy that kind of requirement, okay, always. And this one is actually the idea, okay, of the integration, especially the Riemann integration that we are going to study in chapter 7 of this course as well. Okay, so let us give a proof a little bit of this result. Okay, so if we are going to assume that your f, okay, assume that your f from a to b to, I mean, from a b to the real number r is continuous on its domains, which is the ab. Okay, so by the previous video clip, by the previous section, we know immediately that f is actually uniformly continuous. Okay, what does this mean? It means that if your input is not too far away, then your output is also not too far away as well. So this one, it means that for all epsilon given, there will be the delta epsilon such that for each, I mean, x and y within this domain, okay, and your x and y, as we told you, that is not too far away, then the output of these two inputs, okay, will be less than epsilon that's given. Okay, so let for this one we are going to define the step function, right? And the step function, you need to subdivide the interval into several sub-interval, right? A small sub-interval. So this interval AB as well, we are going to divide it into several pieces, okay? So basically, the idea is that if we have this kind of curve, okay, let me just insert one of the example of the curve of a function f of x like this, okay, and then we got the, you know, the epsilon adding up, or the epsilon subtract down here, okay, we are going to subdivide your closed interval AB into several pieces, and then on each piece we are going to approximate this function by a step function, okay, by a piecewise step function like this, okay, and this one, the error between this step function and the function given, okay, it is within this plus and minus epsilon. Okay, so to do the dividing, okay, we are going to let our m, okay, as the positive integer be sufficient large, okay, integer, so that your h equals to b minus a over m will always less than this epsilon delta, okay, less than this one. Okay, so of course we are going to because the proof, okay, depends on this epsilon, right? So we are going to let your epsilon greater than 0 to be arbitrary, but then by this one we are going to immediately finding this delta epsilon, so that this implication happened, okay. So we are going to let this one, this m, okay, so that the length, so this one will be the length of each sub interval, okay, some interval that we need to divide, okay, will be less than this epsilon delta, okay, that we have from that epsilon, okay. I'm sorry, for less than the delta epsilon that we got from the epsilon that's given, okay. So what we are going to do is to, as we told you, to divide this interval into m disjoint intervals, okay, of length, as we told you, h. All right. So to do that, your I1 right here, this is your first interval I1, okay. It is coming from the left hand side, which is the A, and then because you need your length to be h, so the right will be A plus h, okay. However, if this one is closed and also this one is closed, the next one next to it must be open and then close, open and then close, right? Up to the last one will be open and close as well, so that each of them will be disjoint, okay. So the I1 we need to define it separately. However, for the rest ik, okay, we can define it as a plus k minus 1 h and a plus kh, okay. Your k starting from 2 to that m, okay. So the length of each ik is h, okay. So the length of the ik is h, which is less than epsilon delta, okay. So it means that the difference between these two values, okay, so this is the something that we can notice, that the difference between the two value, okay, within this interval is less than delta epsilon, okay. This is less than epsilon. So we are going to define your sx, okay, and depends on that epsilon, okay, to be f at the point a plus kh. So actually it is the right hand value of f for each interval, right? Okay, so from this picture, for example, this is your first interval, so here's the right hand value. So we are going to define your s epsilon to be this value, okay. For the next one, this is the right hand value, we are going to let your s epsilon on this interval to be this value, okay. All right, so it means that your s will be a constant, okay, on each of the interval ik, right? And if your x it is within this interval ik, then the difference of your f and your s function, okay, actually it is your f of x minus f of a plus kh, right? However, these two values, okay, because your x it is inside this interval, this one is just at your right hand side, okay. So it means that the difference between this value, okay, the length, okay, between them, it is less than delta epsilon, okay. This one is only the input, right, that the length is less than the distance among them is less than the delta epsilon, okay. So it means that from the uniformly continuous here, whenever we got two value of the domain, that is less than delta, the output will always less than epsilon, right? So this one will be less than epsilon by the uniform continuous of the f. Okay, so we are done, right? Because this one is a function f, this one is the step function s epsilon that we construct. Okay, so the two value, the distance among them will be always less than epsilon for each and every x. Okay, so I mean we can conclude a little bit that this one and this one are different, will always less than epsilon for x inside this interval AB. Okay, because don't forget that if you talking about your x in this interval, we need to subdivide your a and b into I1 union I2 etc. up to IM, right? Because we divide this interval a to b into m subintervals. Okay. So if you go further in terms of integration, what we do is that we are going to construct the rectangle, right? The rectangle pieces like this, okay, for each interval here, and then we are going to find the area of each rectangle, and then we are going to say that this area, okay, the area of these rectangular together will be the approximation of the area under the curve, right, and the x-axis from A to B. Okay, so this is something that we got a connection between this approximation and the integration. Okay, however, this approximation just gives you the idea that for each and every curve, right, no matter how small the error that you require, you can find the piecewise piecewise step function, okay, that can be a good approximation of that function always. Okay. However, sometimes you may say that, hey, the piecewise step function like this, okay, may be not that good. Why is that? Because it's not continuous. The approximation is not really continuous. Can we change the piecewise step function, okay, into something that continuous? Okay, so the next idea is that we are going to, if we have given curve like this, we are going to again subdivide into several pieces, okay, and then for each pieces we are going to approximate it by the linear function, a straight line connecting each dot like this. Okay, connecting each dot like this. Sometimes we call this kind of approximation as a spline function. Okay, can you see it as a spline, like the spline cord on your back? Okay, so it look like a spline bone on your back, right, that has like several corner connection here. Okay, so this is the main idea of this name. Okay, so let us talk about the definition first. We are going to say that a function g is a piecewise linear on the interval AB if your AB again can be written as a finite union of a disjoint intervals I1 to In, such that each interval, your g, is actually a linear function, and a linear function is simply like ax plus b, okay, in this form. All right, so again, this theorem saying that if we are given a function f, okay, which is a continuous function on the closed interval AB. And as we told you, this one is actually the application of the uniformly continuous. So if your f is continuous on the closed interval, your f immediately uniformly continuous on that closed interval as well. So no matter how small the error that you need, you can always find a linear function, okay, piecewise g epsilon, okay, such that the approximation here, this one again, it is the approximation value of your function f, okay, and the real value, okay, the error is less than that epsilon that you need, okay. So let us try to give you a proof, but you may say that hey, actually it is the very similar to the previous one, okay, 5.4.2, but instead of each one of them defined as a constant, then now this one of them will define as a linear, okay, as a linear function. Okay, so we are going to use the same idea, okay. So again, your f from a to b, I mean from ab to r is continuous, okay, on this closed interval, immediately uniformly continuous on the closed interval AB, okay. And by uniformly continuous, then we got, you know, the, if we let your epsilon greater than 0, which is this epsilon, but by this uniformly we can find your delta epsilon, okay, such that if your x and y, it is the element in the domain and it is not far away, okay, it the distance among them is less than delta, then the distance among the output will be always less than your epsilon, okay. This one we may need to adjust later on, okay. Let us keep it as the epsilon first, okay. So again, as we did it previously, we are going to let m, okay, be sufficiently large, okay, so that the length of each interval, again, your h, okay, b minus a over m, will always less than delta, okay. And we do the same thing, we divide, okay, each the interval AB into m disjoint interval, okay, of this length. All right, again, I mean, if we talk about two elements in each subinterval, then the distance among these two will always less than delta, right? And again, because your I1 will be the first one, so we have a and a plus h, okay, but your ik, okay, from I2 etc to Im will be the open interval, a plus k minus 1h and a plus kh, okay. So this one from 2 to m. So basically the idea or the picture, roughly speaking, will look like this, okay. So you got your function, okay, and then this is the plus or minus epsilon of that function, and we are going to approximate this function by connecting the dot, okay, between each of the function value on each interval. All right, okay, from the left end of the subinterval to the right end, and then from this left end to another right end, and then to the another right end, okay, up to the last one. All right, so on each, of course, on each interval ik, we are going to let your g epsilon x be a linear function, okay, joining, so it's just a straight line that's joining the point a k minus 1 h f of this point, sorry, this is a plus, then this one is also a plus k minus 1 h. Okay, this is one of the point here on the left side, and the point on the right hand side, which is kh and a plus kh. Okay, so joining these 2 points together, okay, for each k starting from 1 to the last one m. Okay, so your g epsilon is continuous, right? So your g epsilon, because it is joining from your left end to the right end, so it always continuous, is it? Okay, so g is continuous and piecewise linear on the interval a to b. Okay, and in addition, if your x it is in each subinterval, your f of x subtract this endpoint, okay, the left end, and your f of x subtract the right end, okay, the distance between them. Again, here your x it is inside the interval, right? So this one, the input, okay, the distance among these two inputs will less than delta. The distance among these inputs will less than delta. So this one at the beginning, if two input, okay, the distance less than delta, the output will always less than epsilon. So let me just put it as epsilon first, okay, but later on we may adjust, okay, we may adjust. So how are we going to approximate or to calculate this one? Because we are the last thing that we need to do is that the distance between the real function f of x and the approximation, which is piecewise linear, okay, this one, the distance must be less than epsilon, right? So we really need this, okay. So what we are going to do, okay, is actually to determine the difference between the f and the g. So we really need to know what the g is, right? Okay, right here we're saying that your g epsilon is a linear function that's joining this point and that point, okay. So you may think of, okay, to find a equation of the line joining 2 points, you can just do the, you know, the slope and point form, right? You can use a slope and point form, or you can think of it this way. So let me just give you one more page, okay, and we still having the problem with g epsilon, right? So let me just do it right here. If you have your xi, okay, and f of xi joining by a straight line to xi plus 1 and f of xi plus 1, okay, just like this, okay. One way, as we told you, to find the slope m and to use the point slope form, okay. The other way is that we may say that let's talking about a function like this, okay. So this one, let me just put the x sub I over xi plus 1 minus x sub I, okay. So what was the special character of this function? If you plug in xi, this one it is 0, right? If you plug in xi plus 1, this one is immediately 1. Can you see? Okay, so I mean if you plug in f at xi plus 1, this one I going to multiply this function by the value xi plus 1. Okay, I'm going to multiply this function by a value f at xi plus 1. Another one, let me just do xi plus 1 over xi minus xi plus 1. Do we have the same character? If we plug in fi plus 1, you got 0, right? However, if you plug in f sub I, you are going to get a 1, okay? So by this xi that you got 1, I'm going to multiply it by x sub I, okay? So let us call this one g of x, okay? What happened? Your g of x is linear, right? Because it has only x to the power 1, okay? And g at x1, what happened? G at xi, sorry, okay? This one goes away and this one survive and it becomes 1. So g at xi equals to f at xi, and g at xi plus 1, okay? This one goes away, right? But this one survive and it becomes a 1. So it is f at xi plus 1. Okay, so this one can be our g epsilon, right? That connecting two of the points that we consider. Are we good? Okay, so we are going to let our g epsilon, okay, to be a plus kh minus x over actually a plus kh minus a plus k minus 1h, okay, and then multiply by f at a plus k minus 1h. Okay, can you connect the dot? Okay, so this one is your left hand side value, which is this one, right? The left hand side value. So we are talking about this part, okay? However, instead of using the variable subtract the given point, okay, I'll just switch, okay, and start from the given point minus the variable, okay? So this one also need to switch, okay? So the given point will be your right hand side point minus the left hand side point. We get and multiply by the value at the left, and then you are going to add your the next one will be this part, right? The right value. So we have your x minus the left given point, which is a plus k minus 1h over a plus kh minus a plus k minus 1h, okay, and multiply by this value on your right hand side, which is a plus kh. Okay, why is that we need to do a switching a little bit? Because this one on your bottom will be the same, and actually both of them equals to h, right? After doing a subtraction, both of them will equals to h, okay? So this one is our imagination. This is our scrap paper. So let me start from here, okay? Okay, so your f subtract your the whole thing here, okay, the whole thing here is your g epsilon, right? Okay, so if we do a direct subtraction, even though we have this kind of idea that hey, the f of x minus f at the left end and the f of x minus f at the right end should be, you know, less than epsilon, okay. However, this one we got only one of the f, but it seems that on this setting you need two of the f of x. So how can we create that two? Okay, it actually came from this thing, okay, this function that you just creating here, okay. Okay, the function that you just create here, okay. If you just take a look at this one and this one only, okay, what is a special character of these two? As you add them up, okay, as you add them up, the uh, the the x, okay, as you add them up, yep, because this one your bottom are not the same, right? If you change your bottom to be the same, then it will be what, xi plus 1 minus xi, and then this one will be xi plus 1 also minus x. So as you add them up, your x and your x will cancel, right? And then you got your xi plus 1 minus xi, which is the same as your bottom. So as you add it, it equals to what? It equals to 1, right? So this one, okay, is actually multiplied by 1, right? So we are going to replace this one as two terms, this term and that term, so that your f from one term is separate into two terms, okay, concerning the thing involved, the f on the left hand side and the f value on the right hand side. Are we okay? Okay, so this one, let me just write down here, okay, connecting the dot here. So your f, okay, I'll just insert this a plus kh minus x over h and x minus k plus k minus 1h over h, okay, and then subtract the same thing here, your a plus kh over h and f at a plus k minus 1h, okay. And then because this is a subtraction, you need to distribute the subtraction here, so it will be at minus x minus a plus k minus 1h over h, and then f at your right end, okay, and take the absolute value. So it means that this part can combine and this part can combine, okay. So we are going to separate it, okay, into the a plus kh minus x over h, okay, and then f of x, subtract your f on your left end and x minus a plus k minus 1 h over h multiplied by f of x minus f at the right end, okay. Don't forget that right now your x, okay, your x, it is each element in each subinterval, okay, on each subinterval. So on each subinterval, because your x, it is in each subinterval, then what is the distance among the two value in the subinterval, because this one is the right hand of your subinterval, right? So the difference among them will be less than h. So it means that this whole value, okay, this whole value will be less than 1, right? This one as well, your x is in each interval, this one is the left end of that interval, so this one will be less than 1. And this one, what we have given before, the distance among these two less than epsilon, the distance among these two less than epsilon. So we are going to, but what we need to conclude is to conclude that the difference among the f and the g will be less than epsilon. So it means that at the end we are going to adjust your length a little bit, okay, instead of using the epsilon itself, okay, we are going to adjust it by divided by 2, okay, this one you are going to divide your epsilon by 2, okay, so that as you add them up you got the epsilon at the end, okay. So again, if you looking at the difference of your f and your g epsilon for each and every x in the closed interval AB, your closed interval AB, it is I1 union I2 etc. to IM. So we are going to separate your x into each case, right, in each of the subinterval. So on each subinterval you got the difference less than epsilon. Then I mean for the whole interval AB you got a difference less than epsilon as well, okay. So we have this kind of approximation. Are we all right? Okay. So what is it that we got right now? Okay, previously we have the continuous function can be approximated by piecewise constant, okay, and this one as well, a continuous function can be approximated by piecewise linear, okay. Actually this piecewise linear also gives you the idea to approximate the integration in another form as well, which is sometimes we call it as the trapezoidal rule. Why is that? Because each, I mean, instead of cutting as the right end at each of the interval, we connecting two ends of the interval by one straight line, right? So one of the strip that we have it here, it becomes a trapezoid, right? So the area of the sum of the area of each of the trapezoid, okay, will be also another good approximation for the area between the curve and the x-axis in this interval from A to B, okay, and this one is called a trapezoidal rule, okay, of approximating the integration, okay. However, if we keep doing it like this, okay, we can have the most important theorem, okay, in terms of calculus or mathematics, okay, which is called the Weierstrass again, okay, but this one he come alone, okay, it is Weierstrass approximation theorem, okay, which saying that if your interval under consideration is the closed interval AB and your f standing from this closed interval to the real number is continuous, okay, no matter how small the error you can think of, okay, then you can find a polynomial function p depends on that error epsilon such that the difference between the real value and the approximation function polynomial will less than that given error for each and every element in that interval. Okay, this is very important because don't forget that the polynomial we always evaluate a value, right? Even though it may difficult, but we can always, because it depends on multiplication and addition. Okay, but the function maybe we cannot, because it can be a sine function or the exponential function or the logarithm function that if we don't have the calculator, we don't know how to evaluate the value. Okay, so this theorem saying that if you want to evaluate or if you want to approximate the value of function given, then you can approximate it by a polynomial. Okay, within, I mean, and this approximate will be as good as you need. Okay, it is as good as you need. Are we all right? So we are going to close this chapter at this theorem, and we hope that you guys already, I'm not so sure whether enjoy or not, but you have learned a little bit about the limit of the function and also the continuity of the function, as well as some of the application of this, which is very, very important in terms of higher education in economics and also in terms of mathematics. All right, so we are going to stop this video clip right now, and we'll see you on the next chapter. Bye bye.